using standard internet protocols. And then the magic happens when we get to the other end, where we distribute the data via multicast. I'm going to sketch out basically how analysis proceeds when you do this. And this gives you a basic idea of how you're doing it. It's not particularly tricky. The basic idea is that we have some potential signal in the data. And then all we do is we look for some segment of time which we're going to try to analyze. And this data is actually streaming in. And we determine that we're going to analyze this chunk of data when it's available. And some of this you're going to lose. And that's because we have to do filtering on it. People have questions. I can, of course, discuss what kind of filtering we actually need to do. But the point is, we do need to apply filters to the data before we can analyze it. And you lose some of that due to filtering corruption. But we essentially analyze a segment of data. And we produce results for very small chunks, let's say 8 seconds. And what we do is we look for every template in that 8 seconds. And I could talk about how we do that effectively in a second. But then the idea is when we complete this, we've now given you 8 seconds of results, and we try to do that in less than 8 seconds. And then we proceed on to the next chunk. So it's very much, you look at some segment of time, and then you look at the next one, it proceeds very naturally. Now, you could ask, how do we actually do that in guarantee that happens fast enough? Well, the way you do that is we farm it out to many computers. We have a dedicated set of computers just for this task. We use MPI to parallelize this task over multiple nodes, and within each node we use OpenMP to parallelize amongst the processors of those nodes. Each of these nodes is doing a symmetric operation. We're just match filtering a particular portion of the template bank, looking for a certain set of signals, and they report back results to a central place, which we then collect together, see if there's anything interesting, and then submit it on to our central server, which we will then alert astronomers if there's anything interesting. So one thing that's interesting about this is that you can actually do this in only about 160 cores for roughly 360,000 templates, which is how much we needed for O2. That turns out to be relatively tractable. And the whole operation from the gravitational wave passing through our detectors and actually moving the instrument to us being able to report something is roughly 30 seconds. Now, for the past few runs, the longest part has actually been after we see something we have been through a human vetting process. We've actually gotten people together to look at it before we actually alert anyone. But in principle, this is roughly what you can expect down the line. So in summary, we have offline analyses, which are embarrassingly parallel. We use tools like Pegasus, the Open Science Grid, to farm these out to many different clusters. We also do online analyses, which are critical for actually telling astronomers where to point and find electromagnetic signals to our mergers. But these require dedicated resources. And the reason they require dedicated resources is because we need to actually be able to enforce a latency requirement. And you can't do that when you have upwards holistic resources. And I think I'm going to leave you with one last thought. Of course, I do want to highlight some of the open science that people are doing and some of the open software we have. Of course, the LIGO data itself is released through the Open Science Center at lost.ligo.org. It's soon to be renamed WASC, because we have, of course, Virgo joining us, and we'll be also releasing data, and of course there'll be future detectors down the line. The majority of the LIGO analysis codes are, in fact, open source and available for people to use. You can get many of them at lost.ligo.org's software. One of the ones I'm involved with is called PyCBC. You can get information here. We have tutorials, and of course it's available on GitHub. And I think probably with there I can open up for questions. I think probably out of time as well.
Hi, I'm Rich with Inside HPC. We're here at the PASC 18 conference in Basel, Switzerland. And today I'm here with David Bader from Georgia Tech. David, you're giving a keynote tonight about big data, analytics, and graph in the real world. Can you tell us more about that?
Sure, Rich, and I love Inside HPC. Coming to this meeting is fantastic because we see folks in scientific computing and also big data. My talk tonight really resonates on those themes here at PASC 18. I came all the way from Atlanta at Georgia Tech with the Rambling Rex here to Basel, Switzerland, and I'll talk about applications ranging from healthcare. You know, as we get older, we have to worry about a lot more, exactly, and looking at finance, and looking at Internet of Things, self-driving cars. How do we put all of that information and relationships together to make important decisions?
So, David, I'm curious about hardware. I'm a hardware guy, right? In terms of computer architectures, what's holding you guys back from the kind of computation you want to do on this big data?
Rich, that's a great question. Right now, what holds us back is the power spent moving data around. In new architectures, what we're looking at is moving the computation to the data in new memory subsystems. For instance, in the DARPA High program, we're a software performer, and we're working with companies like Intel and Qualcomm to create a new Hive graph processing chip. In that chip, lightweight threads will move around the system to where the data sits and be able to operate more efficiently on these types of challenging problems.
Okay, can you give me one example of the real-world kind of stuff that people would kind of get their handle on this?
Sure, that's a great question. In the real world, we care about, for instance, our health, and we have a lot of electronic patient records, our health records. What I'd like to be able to do is sift through those very fast, of course, with hospitals and medical doctors, to understand preventative medicine and predictive medicine. And that way, our health can be improved by understanding the rich history that exists.
So is this really about finding outliers or predicting the future?
It is. So what we'd like to be able to do is not just take big data and do forensic history as to what happened in the past, but use that in a streaming sense to be able to predict the future and to make decisions rapidly on the fly that gives us a healthier and safer future.
So good afternoon. Thank you for inviting me to this panel. My name is Leonardo Bautista, and I'm going to talk a little bit about efficient multi-level checkpointing. Okay, I don't know how this works. Yep. Okay, so I'm going to start with presenting a little bit what does it mean to checkpoint in high-performance computing, the classical checkpointing strategy that we have used that maybe is not the most appropriate way to checkpoint in current architectures. So I'm going to talk a little bit about deep memory hierarchies and multi-level storage systems, because this is more or less in the direction in which we are moving. So I'm going to talk about some performance analysis that we have done very recently on a machine that has different storage levels, so SSDs, non-volatile memories, parallel file system, and so on. And I'm going to show that it's not always easy to work with these storage levels, and if you don't do it properly, then you don't get the performance that you could expect to get from these new devices. And then from there, I'm going to move to multi-level checkpointing, and in particular, I'm going to talk about the fault tolerance interface, which is a multi-level checkpointing library that I have developed since I was doing my PhD. And I'm going to present some of the new features that we have developed and that are included in the last release of FTI, which was released a couple of weeks ago, and then some future work, and yeah, a little bit of open questions. Okay, so as we already saw in the previous talk, failures are common in petascale systems. This is not deception anymore. Actually, these are frequent failures occurring in petascale systems. So we have to take this into account when we are going to program applications that have to run for many hours and sometimes many days. You have to take this into account to not waste all that energy on all that computing power. Now, also sometimes when a job needs to run for multiple days, in some cases multiple weeks, like the case of climate simulations and this kind of long-running simulations, you have to checkpoint even if you assume that the system has no failures. Okay, and this is because your job scheduler only allows you to run for 24 hours or 48 hours. And then you still have to continue the simulation after the end of the job. So you are forced to checkpoint, and this is not for reliability purposes, but for job scheduling purposes. Okay. So it's clear that checkpointing is not going anywhere. Is needed for multiple reasons, and so the question is how you do it efficiently. Okay. And so the idea is, of course, to take advantage of the new storage devices that are coming into the system that offer new trade-offs. For example, they have much better bandwidth, smaller latency, somehow, in some cases, more capacity than what you would have in DRAM, and so on. But they also have some different, there are different trade-offs. For example, if you are working with SSDs, you have a limited number of writes in each particular cell, so that you have to do wear leveling in order to more or less load balance the writes, and this brings new problems and new challenges. So basically, checkpointing is not as easy as it was, I would say, a decade ago, in which it was just open, write, and close. Okay, this is what we used to do in previous year. We just open a file, we write everything we want to write, and then we close the file, and that is our checkpoint. This is not the way it can be done at exascale. And the reason for that is because we have limitations on the bandwidth on the parallel file system, so we have to do it in a much more clever way, taking advantage of local storage devices. So taking advantage of the storage components that you have in the compute nodes, and then try to asynchronously transfer that to the file system, or apply different techniques like data replication, erasure codes, and so on to guarantee the reliability of this. And so this means that writing a checkpoint is much more complex than just write and close the file. Okay. And the idea behind FTI is to remove all that complexity from the users, from the application programmers, and offer you a library that does all that for you in a more or less easy way. So as I said, you have to deal with multiple storage levels. So let me show you what I'm talking about. So this is the configuration of a machine, a recent machine that we have at the Barcelona Supercomputing Center. It has two IBM Power 9 processors. Each one of those has 20 cores, and so you can run up to 160 threads in each node. These nodes have 512 gigabytes of RAM. It has two SSDs, okay, Micron SSDs, and it has two non-volatile memory, each one with 3.2 terabytes, okay, of capacity. And then in the same node we have four GPUs, NVIDIA Volta GPUs. They have 16 gigabytes of high bandwidth memory. And then we have a single port Mellanox network link, and we have the fiber link to the parallel file system, which is GPFS. Okay, so just by looking at these specs, you already see that there are multiple storage levels. We have the GPFS, we have the DRAM, we have the SSDs, we have the non-volatile memories, we have the high bandwidth memory in the GPUs. So there are plenty of places where data is moving in these new configurations and the new architectures that we are seeing emerging in the landscape of high performance computing. And then the question is how do we use these multiple storage levels in a proper way. In this evaluation, we are mostly focused on the SSDs and the non-volatile memories and the parallel file system. We are currently doing some work with the high bandwidth memory of the GPUs, but I'm not going to present this work in this talk. So to show you a picture of the node, so that you can see we have these are the two processors, the Power 9, and then you see 4 copper plugs, 1, 2, 3, 4 here. These are the 4 GPUs that are located in the nodes. And of course, as I mentioned, you have the DRAM, 512 gigabytes in total. And then we have on this corner, and we cannot see it in the image, here you plug the SSDs. You have 2 of those. And then the 2 bar boxes that you see here are the non-volatile memories that are available in each node. Okay. We did some basic performance measurements, and this is comparing the SSDs with the non-volatile memories. Okay, so what you see on the x-axis is the number of the nodes. Okay, and then in the y-axis is the bandwidth in megabytes per second. All right. You can see that on the top you have the SSDs, and on the bottom you have the non-volatile memories. And then in purple you see the write performance, and in green you see the read performance. You can see that the performance of the solid-state drives is much lower than that of the non-volatile memory. Here we're talking around 500 megabytes per second. In the case of the non-volatile memories, we are seeing up to 3,000 megabytes per second, so 3 gigabytes per second for writing, and over 5,000 megabytes per second for reading. Okay, but so this is something that we more or less expected. We already knew that non-volatile memories were supposed to have higher performance both on writing and on reading. However, what was interesting and was not very expected from this study was these drops in performance for the SSDs. And these were not one-time measurements. Each bar of this one is the average of 6 or 7 tests, and these were consistently low. So there were some SSDs in the system that were consistently performing bad. So in this case, for example, you see 350 megabytes instead of the 500 megabytes that you were supposed to get, and that most of them get. So there are performance differences between the SSDs. Okay, this might be related to aging, to the wear leveling strategies that I mentioned before, similar to the effects that were presented in the previous talk. When the hardware ages, it starts delivering bad performance until it completely fails. So if you have to write a checkpoint in thousands of nodes, it's quite likely that you will end up using one of these nodes that have lower performance. And the checkpoint cannot be assumed to be correct or to be reliable until everybody finishes writing. Okay? And therefore, if you simply compute that you should be able to finish writing in a certain amount of seconds because every SSD has 500 megabytes per second of performance, well, that will not be the case because not all the SSDs will perform at the best because of these reasons. All right? So this is something to take into account when you are using these devices. Now, this is a test that we did for analyzing the importance of the query depth. This means how many processors or how many concurrent writers are writing in the same device simultaneously. So you have the number of I/O operations per second in the y-axis, and you see in blue you have the SSDs, in green the non-volatile memory, and in purple the GPFS. So basically what you can see is that from the moment you reach 8 as query depth, the SSDs more or less, well, still perform. It increased, the I/O operations increase as you increase the number of writers, but the difference is not as important as for the non-volatile memories. If for the non-volatile memories, if you are using only 8 writers, then you will get a much lower performance than if you were using 64 writers, for instance. So depending on which devices you are using, the importance on how many writers you are using simultaneously have differences. There are some important differences there. Now, this is the same for reading. If you look at this figure, the performance that you get with a query depth of 8 is completely different than what you will get with 128 for the non-volatile memory. And that difference is not as big for the SSDs and neither for the parallel file system. So these are just some examples that show that it's not as simple as believing I'm going to use non-volatile memory and everything will go fine. You have to pay attention to how you use them, how many writers you use, and different performance numbers that are important to take into account. So these are some of the complexities that arise when you are dealing with multiple storage levels. In this figure, what we measured was the importance of the transfer size while writing to each one of those different storage levels. So you have in the bottom the non-volatile memories, in the middle the SSDs, and on the top the parallel file system. And the bandwidths are all in megabytes per second, and here you measure transfer sizes that are between 4 kilobytes and 32 megabytes.